about this couple of I'm going to say a few words about this couple of projects that I've done recently with Pratik Agrawal here at Oxford and Mikni, now a postdoc at Harvard. One of them has been almost for 2 years on the archive, and the second will appear hopefully soon. I really hope less than 1 month. So yes, feel free to stop me at any point if you have any question. I don't mind if you stop me. Yes, so before going to the real part of the talk, let me start by showing this slide, which summarizes the main motivation for these projects, which is that imagine that tomorrow we find an axion coupled to photons. I'm going to show this kind of simplified parameter space, GA gamma, the coupling to photons, MA, the axion mass. So imagine we have tomorrow, experimentally, we find a point in this parameter space. So the question is, what can we learn with this point, with this axion coupled to photons? Of course, you can start asking questions like, is this guy dark matter, or does it solve the strong CP problem, which are, of course, very well-motivated questions. What I want to tell you about today is that in addition to this, you can also ask questions like this one about the phi UV of the standard model. You can ask if the standard model is unified in the phi UV. And you can also ask if we can use this information, this axion coupled to photons, to distinguish or even test different kinds of string theory. Good. So just to make sure that we are all on the same page, let me very briefly review what I mean by axions. So for me, an axion is gonna be a compact scalar field with a discrete shift symmetry of this form. Okay, not necessarily the QCD axion. Some people call it axion-like particle. I will call it, in general, axion. Now, the shift symmetry is very important because it totally shapes the kind of interactions that we can have. We can have this kind of derivative. Oh, by the way, do you see my pointer?
Yes, I can see Mario.
Okay, good. So we can have this kind of derivative couplings to fermions. We can have this kind of dimension 5 operators with gauge bosons and this kind of periodic potentials. Okay, everything is shaped by the shift symmetry. Now, in terms of field theory language, usually we say that axions are pseudo-Goldstone bosons of possibly anomalous symmetries. And a prominent example is the case of the QCD axion, which appears after spontaneous breaking of the U1-Peccei-Quinn symmetry, which has a mixed anomaly with respect to QCD. Curly A here is going to be the anomaly coefficient, okay? And it's going to be a super important quantity for the rest of this talk. Now, why axions? You can see that there is an increasing interest in the field about axions, both in theory and experimental, and for experimentalists. And the idea is that they appear easily in many BSN constructions and even in string theory. As I said, a very famous example is the QCD axion, which very fast is just imagine you take the QCD theta term, you promote it to a dynamical field, and it turns out that some QCD effects generate a potential for this field, like the one you see here, so that the vacuum turns out to be CP conserved. So in this way, you solve dynamically the strong CP problem, and in addition, you have a very nice particle, the QCD axion, which is also a very good dark matter candidate, and also experimentalists like a lot this model because it's very predictive. Once you fix this quantity, Fa, which is called decay constant, axion decay constant, almost all the parameters, all the couplings, the mass of the axion, almost everything is fixed. So it's essentially a one-parameter model. So that's why it's very predictive. Now, in the context of this talk, the main motivation for axions is this kind of quantized or topological interactions that they have with gauge bosons, okay? So you can see here this small a, the axion coupled to the GG dual of a gap theory, okay? And what I mean by quantization is the following. While the decay constant F or the gauge coupling alpha, these are dynamical quantities that they run, they depend on the energy scale, okay? They undergo renormalization. Curly A, the anomaly coefficient is just an integer. And this is what this means is that it's quantized in the sense that once you fix it in the UV, it's not affected by renormalization. So it remains constant to the IR. Now, This, together with gauge invariance, I'm going to show you is very important to test the far UV by measuring only trying to search for axions in low energy experiments. And a bit of a tangential point, but I want to mention is that there is an entire program trying to connect some new developments in QFTs, which are called generalized and higher form symmetries, to phenomenology. And what people have realized is that axion couplings, this kind of topological interactions, is a natural playground where these generalized symmetries might have something new to say. Now, whenever someone makes some argument using quantization of some axion coupling or related coupling, you should always have in mind a possible caveat which is related to axion mixing. So let's take the QCD axion. In the QCD axion, you have, as I said, the coupling to photons, which is of this form, AFF dual, with F being the field strength of electromagnetism of QED. So the coupling to photons has two different parts. One is these anomaly coefficients, okay? This ratio E over M, which is topological, is quantized and doesn't run. And the second is this 1.92. This comes from a calculable axion pion mixing. And this depends on the energy scale because it depends on the quark masses. Quark masses run, and it is not constant with, it is not quantized. Okay. So what I want to tell you later is that all the results that I'm going to get are going to be robust, are based on quantization, but they are also robust against axion mixing. I'm going to go into more details later. Now, the main experimental question is, how do we look for axions? How can we discover an axion? So there are several portals or channels to the visible sector in the standard model. A very promising one is the derivative couplings to fermions, these kind of dimension 5 operators that are very important, for instance, in astrophysics. And this is because when an axion couples in this way to electrons, for instance, it can be easily produced in stars, and we get very, very strong, stringent bounds just by assuming that the axion doesn't change too much the stellar evolution. Okay, so you can go to this review by Andrea and Georg Raffel for more details. It's very recent, very nicely written. I won't go into more details about astrophysical bounds. Let me just also point out how you can look for axions in the lab. Okay, so if you take this operator O5 and you go to the non-relativistic limit, what you realize is that you get a Hamiltonian, interaction Hamiltonian, which looks very much like the Zeeman Hamiltonian. You have the interaction of the axion gradient with a spin of a particle, of a standard model particle like the electron. So what this tells you is that an axion gradient behaves very much as an effective magnetic field, and this motivates several kinds of spin precession experiments. So just to mention an example, there is a experimental program called Casper, and they have experiment or a proposal called Casper Wind, which is that if we assume that the axion is the cosmological dark matter, then there is an axion gradient oscillating with a frequency comparable to the axion mass. So you can use the coupling of the axion gradient to the spins to get some sort of axion-induced nuclear magnetic resonance that you can use in your favor to search for the axion. So the way you do it is you have, as you can see here, schematically, you have a detector made of polarized spins, okay? Now you apply a vertical magnetic field and you try to do NMR. You don't know what is the axion mass, but what you can do is to scan with the magnetic field. Because if you change very slowly the applied magnetic field, the resonant frequency will change, and at some point you expect to match the resonance with the axion mass. And at this point, you have a resonant effect, and the magnetization is going to start precessing around the applied magnetic field. So you can try to detect the precession of the magnetization by using a very precise magnetometer. So this is very schematically how Casper Wind want to look for axion dark matter. There are many other options. This is just a very nice example. Yeah, more experimental opportunities to search for axions is through the coupling to gauge bosons. Okay, and in particular, I'm going to remark that the most important experimentally is the coupling to photons, because this allows you to use resonant cavities inside the magnetic field to try to convert a axion that forms part of the dark matter halo into a photon inside your cavity. So the way you do it is you apply a very strong magnetic field, and then you have a resonant cavity that you can scan very slowly with the resonance frequency. At some point, again, I remark that you don't know what is the axion mass. If we know what is the axion mass, life would be much simpler because we wouldn't need to scan, which takes a very long time. Then at some point you keep scanning, you hope to match the resonant frequency, and you will see a peak, a boost in the signal. Okay. Now, ADMX, for instance, is the most famous example. Is trying to search for action dark matter at around the microelectron volt scale. And this, you should imagine the Compton wavelength of this action to be comparable to the size of the cavity. This is also telling you that cavity experiments are somehow limited because you cannot build it too big, and you also cannot build it too small. This is just an approximate way to understand the relevant physics. Of course, the experimental details are very complicated, and you should go to some review like this one by Igor for more details. Good. Let me just mention a last very spectacular signal that you can have in cosmology, which is called cosmic birefringence. So the idea is the following. Let's assume we have a very, very light axion coupled to photons, like this effective Lagrangian. Small a is the axion. Curly a here is the anomaly coefficient, and F is the field strength. Okay. Now, if there is extremely light axion, then because of this coupling, the axion is going to induce a rotation of CMB photon polarization. This effect is called cosmic birefringence and is one of the most promising ways to look for axions in cosmology whenever their mass is lighter than Hubble at recombination, which means that the axion mass has to be smaller than 10 to the minus 28, 10 to the minus 29 electron volts. There are two ways to generate a non-zero rotation angle. One is to have an axion field value that changes between recombination and today, okay, just a slow roll. And the second is to have a population of axion strings in the universe, okay. And as the photon goes around goes through the string network, it will get some rotation angle. Now, the reason why I think this is super exciting is because at the moment there are hints for a possible non-zero rotation angle. Okay, there is a group led by Komatsu that has reanalyzed Planck data, and they find a non-zero value for beta. Of course, this requires further scrutiny of the signal, better understanding of systematic effects and all that. But if confirmed, it will have huge implications for the UV, because precisely these kind of axions, very light axions coupled to photons inducing cosmic birefringence, for instance, are the ones that have a lot of information about the UV, the information that I want to tell you about in this talk.
I'm sorry, one question.
Yes.
Why is it necessary to look at the recombination epoch to look for this coupling in this case? In the previous slide,
well, yes. So you know that CMB photons are emitted when the Hubble parameter is of this order, okay? And what you want to have a non-zero effect, you need that the axion from this integral, you need that the axion field value changed between recombination and today. If the axion was much heavier than this, then by the time of recombination, it would have been already in the minimum. So it wouldn't displace with respect to today, and the signal would be zero.
Okay.
Is that answering your question?
Yes, but or partially, because yeah, this CMB photons, you said it's emitted at recombination. But my question is it possible to look for this type of effects on another experiments?
On other cosmological signals, you mean?
Yes, although, yeah, in the previous slide, you showed this ADMX,
yes,
which measures the same coupling, right? Yeah,
they measure the same coupling, but the physics is
it's different.
super different, right? Here you have the conversion of a dark matter axion into a photon because you are in the background of a strong magnetic field.
Yes.
And here what you have is that the interaction with of photons with the axion induces some neat rotation of the photon polarization.
Yeah.
So,
Okay.
so it's of course the same coupling, and there are many other ways to try to test this coupling. These are just two of the most. It's a biased selection of what I think is a good way to test or look for axions.
Thank you.
Thank you for the question. So yes, I was saying that there is a huge experimental program throughout the world, okay, trying to search, well, not only axions, because this is taken from Kieran's website, and it also contains dark photon experiments and other experiments trying to search for scalar and vector dark matter. But you can see is dominated by green, okay, meaning that there are many axion experiments throughout the entire world, and this makes it experimentally very exciting. Okay, it's not only theory exciting in my opinion, but also there are really realistic experimental chances to in a near future, maybe if we are lucky enough, find one of these particles. In the context of the axion photon coupling, there are many kind of searches that you can do. As I was saying, we have laboratory in red, astrophysics in green, and cosmology in blue. Solid colors are already existing bounds, and the shaded red are the prospects for future experiments. So you can see that a huge new region is in principle going to be covered. How optimistic were people with these estimates or not? I'm not going to enter into details, but if true, there is a huge new parameter space that will be covered. And hopefully a big part of the QCD prediction, which is this yellow-orange band here. Good. So I was talking about possible applications of once we have discovered an axion coupled to photons. And the first application is we can start asking questions like, is the standard model unified in the far UV? So let me give little bit of context why theorists and, well, I think we all believe that unification is an attractive framework. So in the standard model, we already have a few hints that point towards a unified theory. Probably the most striking one is the question, why is the hydrogen atom neutral? Okay? Or why the proton and the electron electric charge cancel to such good accuracy, which demands that all isolated states have an integer electric charge. Now, in theoretical motivation is anomaly cancellation in the standard model, which is beautifully explained in some grand unified theories, and more phenomenological nice predictions are the weak mixing angle, for instance, and some fermion mass relations. Okay. Now, what we have done is to propose axions as a nice probe of way to probe unification. And this is because, as I said, they have this kind of quantized or topological interactions with gauge bosons. So what I want to show you is how you can use anomaly matching arguments and gauge invariance of the UV group, which, by the way, can be your favorite simple GAT, can be SU5, SO10, E6. Everything I'm going to say is independent of the gauge group as long as it's unified in the far UV. So I'm going to show you how you can get strong constraints for axion couplings, totally independent of intermediate scale physics and independent of the symmetry breaking pattern. So the story is the following. Let's take this starting point. We have GGAT, your favorite unified gauge group that can be SU5. We also have a non-specified number, totally arbitrary number for generality of U1 global U1 symmetries, okay, from which we can in principle get Goldstone bosons, and we can in principle assume that some of them have a mixed anomaly with the GAT gauge group. Now, at this point, you should stop and think about a similar situation in the context of the standard model, where we have baryon number and lepton number, both looking anomalous with respect to SU2, but this is just an artifact, is hidden in a basis rotation because you can go to B minus L and B plus L and you realize that only one linear combination is truly anomalous. Now, this is totally general. You can always redefine your symmetries and go to a basis where only one is has a mixed anomaly with GGAT, and the rest are just the anomaly-free global symmetries. So the reason why this is important, that you can perform this field redefinition, is because then you only have one non-zero anomaly coefficient that corresponds to the axiom that couples to gauge bosons, and the rest, the anomaly coefficients corresponding to the rest of the global symmetries, are exactly zero. And because of quantization of anomaly coefficients, they are zero to all energy scales. It doesn't matter what you do to your theory at intermediate scales, if you integrate out particles, if not, if you have some symmetry breaking pattern or another, you know that the anomaly coefficient cannot change. In terms of currents, what this is telling you is that the currents with which are anomaly free, they are going to give you Goldstone bosons which are totally decoupled from gauge bosons. And only one linear combination, the one I'm calling U1PQ, has a non-vanishing divergence proportional to GG dual. And this is the guy that is giving you an axion coupled to both, necessarily both, by gauge invariance, photons and gluons. So in other words, topology of the axion couplings plus gauge invariance of the full GAT theory is telling you that in GATs, in grand unified theories, the only axion that can couple to photons necessarily couples to gluons, and therefore unavoidably you get a QCD potential. Now, I haven't tell you anything about the decay constant. The decay constant is very important to know in the context of the QCD axion to know the mass. But at this point, I haven't said anything. But what these arguments are telling you is that you don't know where exactly, but the axion coupled to photons in the context of GATs necessarily lies on top of the QCD band. Okay, just because of this argument. So once you have the result, you can start asking, can I modify my theory? Can I do model building, axion mixing, axion-like axions, additional gauge bosons, extra dimensions? Everything you're gonna achieve is to populate at most additional axion-like particles to the right of the QCD band. So what this means, okay, is that the coupling of any axion-like particle over the mass is bounded by the coupling to mass ratio of the QCD axion. Okay? In other words, there is no possibility of having an axion-like particle to the left of the QCD band in the context of unified theories, meaning that if you discover an axion here, okay, like in one of these experiments, like in WISP LC, for instance, this axion is incompatible with unification. It doesn't matter how much model building you do, this is incompatible with unifying the standard model.
Sorry, can I ask you
Yes.
once again about the symmetries in the previous slide? Because you said you can choose what, yes, or maybe the other, the previous, yes. So you have the GAT symmetry and an additional U1 global, those are global symmetries.
Yes, I have a non-specified number of possibly arbitrary number of global U1 symmetries that I can break spontaneously, giving me Goldstone bosons, and I start asking how many axions coupled to gauge bosons I have.
Okay.
And the point is that if they are exact, they are not explicitly broken, you can always go to this basis, where the mixed anomaly with the GAT gauge group is saturated by a single linear combination of axions.
So they are not explicitly broken, you said, but there is a potential that was...
sorry, yes, only one linear combination, the PQ linear combination, is going to be explicitly broken by instantons. Yes, there is a potential induced QCD. As you can see in this divergence of the current, only one... The correct statement is to say that only one linear combination of U1 symmetries has a non-vanishing divergence.
Okay. Okay, thank you.
Good. Any other question before I move to the second part? Okay. So yeah, that was related to grand unification. And part of work in progress that I'm doing at the moment with Pratik and Mick is that we can also start asking questions about possible UV completions in the very far UV related to string theory. Okay, and in fact, I'm going to show you that an axion coupled to photons can give you a lot of information. Good. So almost any string theory talk is going to show you this kind of cartoon at some point. And this is for a good reason. So at the moment, I think it's fair to say that string theory is one of the best, if not the best, understood framework that is able to unify gravity and particle physics and describe gravity in a quantum framework. And what this cartoon is showing are the different weakly coupled string theories that are related by a network of dualities. Okay, so it was very attractive for theorists many years ago to discover that these string theories are actually related by a network of dualities, despite they look very different. Like type 2 theories with where you can have intersecting branes look very different from closed heterotic strings, for instance. So today, I'm just going to restrict myself to these string theories, in particular to heterotic strings C8 cross C8 SO32, which is dual to related to type 1. And the reason why I'm going to restrict myself to this is because in these string theories, the gauge group is fixed by anomaly cancellation. UV consistency of the theory automatically fixes the gauge group in 10 dimensions to be SO32 or E8 cross E8. And as I'm going to show you, this is in one-to-one relation with axion couplings, and it's going to allow us to get a lot of information about the far UV just by doing low energy measurements. Okay, and in particular, for simplicity, I'm just going to restrict myself to E8 cross E8, because anything that I will say for E8 cross E8 is going to apply to SO32. Good. So now the main question is, of course, how can we test string theory? Because people say for a good reason that these theories are very, very hard to test and probably even hard to falsify. And this is because any quantum gravity effect is going to be suppressed by Planck mass, which is a huge scale, and even more exotic effects like production of some stringy object like cosmic superstrings or some sort of branes in the very early universe seems implausible due to the high tension of these guys. So what I want to remark here is that this is of course true, okay? I just want to say that axion couplings are very special couplings. They only depend, as we saw before, they only depend on a few topological data in the far UV, which in the end are going to be just a bunch of integers. And there is a huge experimental program. So they are in principle measurable in practice. So the goal is to see how can we get non-trivial tests for string theory, or at least some string theories. So just to make sure that we are all, again, on the same page, there is a lot of literature about the stringy axions since almost 40 years ago, since the very early days of heterotic strings, people have considered axions. And this is because in string theory, there are multiple sources that can give you axions in the 4D EFT. A prominent example are p-form fields, Ramon fields, okay, that correspond to generalized in some way. They generalize the notion of a gauge potential. Also, the B field, which is present in all string theories, is going to be giving us axions in the 4D EFT. And more or less the general understanding is that when you take a p-form field and you integrate it over a closed p-cycle in the compact space, in the 4D EFT, you get an axion. You get a particle that only has derivative couplings, is massless to all orders in perturbation theory, and can be coupled to instantons can be coupled to gauge bosons through topological coupling. Okay, and this defines what I will call a stringy axion. Now, what people kind of discovered 15 years ago realized is that most of the compact manifolds, most of the compactifications that people have considered as realistic compactifications have a very complex compact space. And it turns out that the number of axions is in one-to-one correspondence with this complexity, because the more, the higher is the number of non-equivalent compact cycles, the higher is the number of axions. Okay. Now, there is a huge effort, both mainly in theory, trying to understand properties of string theory axions, and this is also because they offer a very nice explanation to why the axion quality is good enough to solve the strong CP problem. And it's because since the axion in some sense comes from a generalized gauge field in the compact space, then any explicit any source of explicit breaking of this shift symmetry is going to be exponentially suppressed. So the quality of these associated axions is going to be exponentially good. These are of course modulo a very important caveat, which is that we don't understand yet, we don't have a standard model of moduli stabilization that could ultimately spoil the flatness of the axion potential. Okay. Now, you can ask, axions in string theory have been there for 40 years, okay, since the early papers by Witten and others. So what is new here? So what I think is new here is that what we have realized is that in some theories where UV consistency fixes the UV gauge group, then you can use the topology of axion couplings to get very stringent constraints in the 4D EFT. And this is because once you take your 10D axion, your 10D supergravity axion, you can show that you can unequivocally match the 10D supergravity axion to the 4D EFT at the compactification scale. And since you know that axion couplings don't run, then the shape of the axion couplings is going to be preserved in the 4D EFT at arbitrarily low energies. Okay, so the idea is to, in this cartoon, is to match the 10D supergravity axion to the effective Lagrangian at ADMX scale. So what I'm going to show you is that this process allows you to get very well-defined predictions for axion couplings to photons, which are totally independent of some details of the compactification, such as how do you get the standard model spectrum, okay, which is the most important part. And in fact, in some string theories, very well-motivated constructions, you still get this bound, that the coupling to mass ratio is bounded by the QCD axion scale, the QCD axion coupling to mass ratio. Okay, good. So just a very quick summary about heterotic strings. I just need to know that it is a theory of closed superstrings in 10 dimensions. And the most important concept is that the anomaly cancellation mechanism that Green and Schwarz discovered fixes the UV gauge group to be E8 cross E8 or SO32. Okay, now you have an effective action given by 10D n equal 1 10D supergravity, which contains the following massless spectrum. It contains the metric and the moduli fields. Okay, the gravity supermultiplet also contains the so-called B field, which is fundamental for me because it's the source of axions, and the dilaton, which fixes the string coupling. In addition, of course, as usual, we have the Young-Mills supermultiplet with the gauge bosons and gauge GNOs giving us charged matter in 4D. But this is not important for us, for axion physics. Now, why do I say that Green-Schwarz mechanism is crucial? So in this anomaly cancellation mechanism, we have terms of this type, okay? B wedge trace F square wedge trace F square, which are crucial to cancel 10D anomaly. It turns out that when you integrate over the compact space from this term, the same that cancels the anomaly, gives you an axion coupled to gauge bosons in 4 dimensions. Okay, that's why I say it's crucial to understand the anomaly cancellation. Now, of course, you can ask, it is true that the UV is very simple, there are only 2 possibilities, but there is a huge spectrum of many possible EFTs that you can get, because you have a lot of freedom to choose the compact manifold, a lot of freedom to choose possible Wilson lines and other shifts and other sources of symmetry breaking, and you therefore get many possible for the EFTs. In fact, you can get many different gauge groups, some of them not even unified. You can get from 0 to whatever number you want of chiral families. You can get a huge spectrum of IR theories. So how does this make sense? The idea, as I said, is that axion couplings are still topological here, and I can match the couplings straight from the 10D supergravity action to the 4D EFT at low energies. Okay, and this is going to be totally independent of intermediate scale physics. And I'm going to show you now that the results in the end only depend on a discrete choice, which is how do you embed the standard model into E8 cross E8. Okay, so this is going to be the crucial point. Now, what is a stringy axion? How does it look like? In field theory, we know that is the phase of a complex scalar field. We break spontaneously a global U1 global symmetry, and we get an Ambu-Goldstone boson. If it is coupled to instantons, I generate some potential, and that's how I get a axion field. It turns out that in string theory construction is quite different, but it can be understood with a toy model, which is a field theory, a gauge theory in 5 dimensions. So let's imagine we have QCD cross U1 in 5D. Now, the U1 is very important because the 5th component of this vector boson is going to give us the axion in the 4D EFT. So what we can do is the following. We take the 5D bulk, where we have QCD cross U1, and we compactify the 5th dimension on an orbifold, which is a circle, S1, modded by a discrete parity. We can choose the boundary conditions to get massless gluons in the 4D, and also a massless pseudoscalar, B5. It turns out, okay, that because of the gauge invariance in the 5D bulk, this guy, B5, has a flat potential. It cannot get a mass, because if you add a term, a local operator generating a mass for this guy, this is not compatible with the gauge symmetry in the bulk. Okay, but there is a term which is called Chern-Simons term that you can write in 5 dimensions, and it involves the gauge boson of U1 coupled to gluons like this, with a coefficient in front, K, which is an integer, and it's actually related to the anomaly coefficient, because when you integrate this over the 5th dimension, what you get is this kind of axionic couplings in the 4D EFT. Okay, so this guy B5 for a 4D observer, for a 4D experimentalist, actually looks like a QCD axion, even though it came from a U1 gauge field in 5 dimensions. Now, you can ask if there are explicit shift symmetry breaking effects that could spoil the solution to a strong CP problem. And the nice thing of this framework is that you can show that these kind of terms are always exponentially suppressed like this, with the instanton action S, which is 2 pi capital M times R. R is the size of the extra dimension. M is the size of the cutoff of your theory. So this can be made much larger than 1, so that any non-perturbative effect breaking the shift symmetry of B5 on top of QCD is going to be exponentially suppressed. Now, this was the toy model. In heterotic strings, for instance, the thing is a bit more complicated. As I said before, the source of axions is the B field, which is a 2-index antisymmetric tensor, is a 2-form. Okay, And it is also important that we have a 10D dual of B2, which is a B6, which is, in other words, is a 6-form field. So this tells you that from these two objects, I can get many axions, but I can classify them in two classes. I have a single model-independent axion, which I get from integrating B6 over the entire compact space. It is a 6-form, so if I integrate it over 6 compact dimensions, I get an axion in 4D. Now, the compact space is 6-dimensional, and in 6 dimensions, you can have many inequivalent 2 cycles. So depending on how is the compact space, you can integrate B2 over many possible 2 cycles, telling you that you in principle can get many different model-dependent axions. It is called model-dependent because even the number of cycles does depend on the compactification, does depend on the model, okay? So these are the two kinds of axions that I have in heterotic strings. I also have shift symmetry breaking effects, but because of time constraints, I'm gonna go a bit fast. I will just say that they are always exponentially suppressed. So you expect, maybe not all of them are light, but in general, you expect to have a handful of good quality axions. So now the important part, how do we get the 4D, the axion couplings in the 4D EFT? So it turns out that you get all of this from the bosonic part of the 10D supergravity action. Don't get scared about the wedges and all that. The important point here is that we only have these two terms. The first one involves the topological couplings of B6, okay, to all the gauge bosons in the theory. Trace 1 and trace 2 stand for the first and the second E8, okay? And F is the field strength of the E8 gauge symmetry. The second important operator or term is this B2 wedge X8. This is very important because this is precisely the Green-Schwarz counter term, which is crucial to cancel anomalies. So the upshot is that when we integrate these two terms over the compact space, we are going to get axionic couplings in the 4D EFT. So consistency of the theory tells you we have axion couplings in the 4D effective theory. Written in terms of effective Lagrangians, what we get is the effective Lagrangian for the model-independent axion. As I said, now we are in the 4D EFT, so trace 1 F square turns into the sum of the unbroken 4D gauge groups that come from the first D8. Trace 2 is the same, but with the second D8. Now, the model-dependent axion effective Lagrangian is a bit more complicated. There are several anomaly coefficients. These integers k are calculable anomaly coefficients that depend on the compactification, but you can easily compute them. The important point is that what doesn't depend on the model is that each of the individual BI, each of the model-dependent axions, couples to the entire trace 1 F square or to the entire trace 2 F square. And this is the important bit, because this is what allows you to combine both effective Lagrangians into the most general effective Lagrangian, and you realize that despite you can have 100 axions, 100 model-dependent axions, at the end of the day, you only have two independent linear combinations, theta 1, theta 2, coupled to trace 1 F square, couples to and theta 2 coupled to trace 2 F square. So this is the important bit. And the reason why this is important is because once you achieve this, this is telling you that all the phenomenology at low energies, in particular, well, and all the phenomenology, I mean the coupling to gauge bosons, ultimately depends only on how we embed the standard model gauge symmetry into the UV gauge group. Okay? And now we only have two options. We either take the standard model and put it into the first E8, or take the standard model and have a non-trivial embedding into E8 cross C8. So let's take the first option first, which is the standard embedding into the same E8. This is called the standard embedding because it's what people consider at in the early days of heterotic strings, and the main motivation is because it's much easier to get the standard model in this way. Okay, I'm not gonna care about how I get or not the standard model, because what this result shows you is that it only cares about embedding the gauge symmetry into E8 cross E8. I don't care if I get 3 families or I don't get any family at all. Now, let's focus about this possibility. So what we have is that we take electroweak sector and QCD and put it into trace 1 F square. So for couplings to gauge bosons and in particular to the photon, we only need to care about theta 1. As I said, theta 1 can have a very complicated structure, can be a linear combination of a large number of axions, but it doesn't matter because it's a single linear combination, it's a single physical axion in some sense. Okay, and you can see this at the effective Lagrangian level, because what you have below electroweak symmetry breaking scale is that the only axion, the only linear combination that couples to photons, FF dual, is theta 1 necessarily couples to QCD. Now, all the string effects, all your ignorance about what's going on with the second E8, what's going on with the possible stringy instantons, what's going on with the compact space is codified into an effective potential for the model-dependent axions, but you only have a single linear combination, meaning that any other couple to photons, meaning that any other axion that is not inside theta 1 can only couple to photons if it arises through mixing with theta 1. And when you have a mixing induced coupling, it is necessarily smaller than the initial coupling, meaning that if theta 1 couples at 3 level to photons and I mix some other axion to theta 1, I get a mixing induced coupling for the second axion, but it has to be necessarily smaller than the coupling to theta 1. So at the end of the day, what you get is, to lead in order, only the QCD axion couples to photons, and any additional axion or axion-like particle necessarily satisfies this bound. So again, we are left with the same bound as with 4-dimensional GATS, regardless of all the complexity in the compactification and all that. If you discover an axion to the left of the QCD band, or you see cosmic birefringence or ultralight axions couples to photons, you rule out the standard embedding in heterotic strings. It doesn't matter how complicated is your compact manifold. If the standard model is embedded into the same E8, this is not compatible with the cosmic birefringence signal. Now, this is a super strong statement, so one has to evaluate any possible loophole. Okay, what are
Mario,
possible?
sorry.
Yes.
And what happened if this is embedded, for example, in SO32? Because you were also mentioning about SO32 in a string, heterotic string. The result
Yes,
will be the same?
the result is the same. Yes, and in fact, so yes, SO32 is totally, the result is totally equivalent to the standard embedding of the standard model into E8 cross E8.
I see.
Because what you would have actually is, instead of trace 1 F squared trace to F squared, you would only get one trace of F squared. So you only have one linear combination. You never have two possibilities here.
I see. Thank you.
Yeah, thank you for the question. Yes, I was saying that one has to consider possible loopholes and have a critical understanding of the situation. And there is a possible loophole, which is the non-standard embedding of the standard model into E8 cross E8. Because schematically, what you can do is to embed QCD into the first E8 and part of electromagnetism into the second E8. In this case, theta 1 would be approximately a QCD axion, and theta 2 would be approximately an axion-like particle that doesn't talk to gluons at all. Now, in more detail, what this looks like is like this cartoon here. You get SU3 cross SU2 cross a bunch of U1s from the first E8 and this other group from the second. And then, for instance, you can Higgs to the diagonal different U1s in different E8s to get hypercharge. This would give you an ALP. Now, you know for sure that in the second D8, there are some sources of instantons. So you have an ALP potential for theta 2. Okay, the question now is, how is lambda alp compared to lambda QCD. So it's a model-dependent question to know if the alp line is to the right or to the left of the QCD band. It's a model-dependent question because it depends on which instantons we have in E8, in the second E8, for instance. Now, there are model-independent implications of this non-standard embedding. And this is because whenever you embed hypercharge in a non-trivial way into both E8s, you know for sure that the weak mixing angle prediction is modified. You're not going to have 3/8 at the gut scale anymore. And most likely you're going to have some value which is smaller than 3/8. Now, if you ever have done gut model building, you know that modifying the weak mixing angle is usually bad because then you need a quite non-standard running of the gauge couplings to match the observed values at the weak scale. It's not impossible, but you have to deal with it. The second can be more problematic, and it's because whenever you have a non-standard embedding of the standard model, you know for sure that you have fractional charges. It turns out that in many cases, these fractionally charged states are very heavy, so it's not problematic. You just need to get rid of them in the very early universe. But it can happen that in some models, these fractionally charged states are chiral. And if they only get a mass after electroweak symmetry breaking, then you are in trouble because we know these guys cannot exist. So just to conclude, let me just say that it is very exciting that we have a very developed experimental program trying to search for axions coupled to photons, because on top of the standard questions like related to dark matter and the strong CP problem, we can also get very valuable information about the UV. Okay, and in particular, it's very exciting that most of the planned experiments are going to look for axions precisely to the left of the QCD band, as you can see in this plot. Okay, this is precisely the region where you don't expect axions in grand unified theories or in heterotic strings. So it is a very non-trivial test for these theories. I just want to say that we cannot confirm unification or we cannot confirm heterotic strings by finding an axion, but I do believe that axion searches can offer very non-trivial tests. Thank you.
Thank you very much, Mario, for the very nice and very complete talk. Question from the audience?
I have a question. Well, several questions, but
Yes.
let me ask you a few. If string theory predicts that the axions should be at this in this orange diagonal line, and below that, shouldn't we be looking, or the experiments shouldn't be looking in that region?
Yes, but it's much more complicated. So yes, well, my opinion is that we should cover all the QCD band. That's for sure. And if possible, go a bit beyond it. But just imagine you fix the mass to a given value. Being to the right of the QCD band means for a fixed mass, smaller coupling. And this is always going to be more complicated. Yeah.
That's true, but if you go to higher masses, like 10
Yeah,
to the minus 1, in
yes,
principle, you can get.
but going to higher masses, then you have to do different experiments, and maybe these experiments are complicated. So IAXO, for instance, is a very promising way to cover part of the QCD band at the high mass limit or N. And also nicely, they are going to be dark matter independent because they are looking for axions produced in the sun, right? So I think it's a very promising way to search for axions. But in my opinion, one should cover all the band,
Sure.
of course, try to cover all the band. Yeah.
Okay. And my second question is, Well, I'm not too familiar with string theory and all these UV completions of string theory, and when you embed the standard model. And what about if we, let's say, we find out that there exists a new a second Higgs, let's say, of 1 TeV of mass. So we get an extended Higgs sector, let's say. What happened with all these UV or string possibilities, string theory possibilities? Are going they are going to change somehow, or
well,
that is independent of?
at least the things that I discussed today, which is essentially how to match 10D supergravity, the axion couplings that you get from 10D supergravity to the 4D EFT at low energies, is totally independent of intermediate scale physics. So you can have an extra Higgs at the few TeV scale or something like that, and it will not change the results. All this all this follows from quantization of axion couplings. So they are totally insensitive to whether you have more or less degrees of freedom at intermediate scales. They are totally insensitive to that physics. Ultimately, the only physics that can change your axion couplings is how you take the standard model and put it into E8 cross E8.
Okay. Wow. It's very general in that sense, this type of predictions.
Yeah, I think so. Thank you.
Thank you for the presentation.
More question from the audience?
Yes, I have a question.
You continue.
First, thanks for the nice talk, Mario. Really nice.
Thank
Just a curiosity, in that plot that shows the experimental bounds and sensitivities, there seems to be a region around 10 to the minus 3 electron volts or so, that the experiment seems to be blind to the,
yeah.
is there a physical vision for that in this specific
That's a very
masses?
good question. So at those mass, okay, I'm not an expert on the experimental part of the axion photon coupling, but I believe that in that regime, all your ideas to search for axions using resonant cavities and all that start to fail. I don't know what are good strategies to search for those axions around milli-electron volt, but it is true that it's a very, very important region. And the reason is that if we, for instance, have post-inflation breaking, okay, breaking of PQ symmetry spontaneously after inflation, we can have axion strings and axion domain walls. And when you take into account this contribution, it pushes the mass to higher values, and it's actually close to milli-electron volts. And it's precisely where we have less experimental idea. The main reason why we don't have good ideas, I don't know it, but I know that people really would like to cover this region. If they don't have good ideas, it's because it's hard. Yeah.
But why, when we have strings and stuff, this will push the masses
Because they
higher?
generate addition. So on top of the usual axion coherent oscillations around the minimum, the decay of these topological defects introduces extra contributions into the relic density. And in fact, they dominate the relic density. So what this means is that for the same abundance, you require a lower decay constant, and lower decay constant for the QCD axion means larger mass.
Okay, but you assume that those topological effects are generated and then decay somehow.
Yes. They do decay because of the turning on of the axion mass. This creates domain walls between strings, and therefore the whole network annihilates. It could happen that there is a stable network, and then you should make it decay through some other effect. But this is a bit more involved in that case. Yeah.
Okay, okay.
There is a huge effort by some groups like Giovanni Villadoro and Ed Hardy trying to estimate very precisely the contribution from the string wall network, because it's very important in the sense that post-inflation breaking is very predictive. So if you come with a very good prediction of what is the mass, then you can tell the experimentalist. The experimentalist can set up some resonance search precisely at this frequency, and it's much easier than keep scanning a very broad range of masses.
Yeah.
That's why if someone could come from the future and tell us what is the axion mass, you could discover the axion tomorrow, probably. But
If you know precisely the mass.
yes, it's much easier, but we don't have that information.
Okay. Okay, thank you.
Thank you. Yeah, that's a very good question.
More question from the audience? If there are no more questions, we say Mario for the very nice talk. Mario, thank you very much for the very nice talk.
Thank you.
And we meet at the next seminar. Thank you so much, Mario.
Thank you.
Bye.
If anyone
Bye-bye.
has further questions, just send me an email. I'll be very happy to chat or, yeah. Thank you.
Daniel, are you going to ask you want a question? Do you have
No
more questions?
No, it's bye. Sorry.
Okay.
Have a nice
Bye-bye.
time, all of you. Bye.
Take care.
Bye-bye.
Bye-bye. Thank you.
Bye.
Take care.
Take care.